Electrical cables are routinely connected to many different types of equipment to serve a variety of functions. When these different connections are made, the cable has to be terminated or ended at the connection point. The preparation for these terminations and several of the ways by which these terminations can be made are the subjects of this training program. Knowing what terminations are, how they work, and how they can be installed correctly is essential for anyone who will be working with high voltage cables and equipment. When a cable is connected to a piece of equipment, the cable has to be terminated or ended. Terminations are similar to splices, but they're used to connect cable ends to other equipment rather than to other cables. And just as there are different types of cable splices, there are also different types of cable terminations. In this first part of the program, we'll see how terminations can be classified and what each class of termination provides. To understand what terminations do, you need to know how a cable is designed. For this program, we'll only be concerned with primary cable terminations. So let's look at how a primary cable is constructed. In earlier training, you learned that a primary cable typically consists of a conductor, a semiconductive conductor shield, primary insulation, a semiconductive insulation shield, and a metallic shield. In some cases, the cable may also have an additional outer protective jacket. Each one of the primary cable layers serves a specific purpose. When the cable is cut to be terminated, the cable layers are removed to expose the conductor so that a connector can be installed. Then a termination is installed to help the cable function properly in the areas where the layers were removed. There are three basic classes of cable terminations: Class 1, Class 2, and Class 3. A Class 1 termination provides three things. First, it provides voltage stress control for the cable's primary insulation. Secondly, it protects the primary insulation against damage from external leakage or tracking. And finally, it provides a seal for the end of the cable to protect it from the environment. A Class 2 cable termination provides stress control and tracking protection, and a Class 3 cable termination provides only stress control. The type of termination that is used on a particular cable generally depends on the severity of the environmental conditions to which the cable will be exposed. All three classes provide voltage stress control for the cable's primary insulation layer. Let's look at a simplified illustration to see why stress control is important. This is an illustration of a primary cable with the cable jacket removed. When a cable is terminated, the semiconductive insulation shield, which is in contact with an electrical ground, must be kept at a safe distance from the conductor and connected equipment to avoid a direct path to ground. So the semiconductive insulation shield is cut and moved away from the end of the cable conductor. When this is done, there is no voltage stress control beyond the point where the shield layer was removed. As you can see, the stress lines run from the conductor straight through the insulation where the insulation shield is present. But where the insulation shield has been removed, the stress lines curve back toward the end of the shield area. Voltage stress is concentrated at this point. Without some form of stress control, the insulation could become overstressed and fail. Cable terminations use two different methods of controlling voltage stress. One method involves increasing the thickness of the insulation, and the other involves changing the cable's electrical field. With the first method, the cable insulation is increased at the end of the insulation shield layer by building a cone of insulating material. The insulation shield is then extended to the high point of the cone with semiconductive tape. The addition of these two materials decreases the concentration of voltage stress. It does this by providing increased insulation at the end of the insulation shield. The additional materials increase the distance between the insulation shield layer and the conductor. This distance is called creepage distance. The increased insulation more evenly distributes voltage stress, effectively eliminating any concentration on the cable's insulation. Another method of voltage stress control is to apply a stress control material to the insulation shield. The stress control material changes the cable's electrical field. We'll be learning more about this method later in the program. As mentioned earlier, each class of termination provides voltage stress control. However, Class 2 and Class 1 terminations both provide tracking protection. Tracking is leakage current flowing between the conductor and the grounded insulation shield. Tracking can result from a combination of voltage on the conductor, contamination such as dirt on the outer layer of the termination, and moisture. Sometimes it's necessary to seal a termination to protect it from water and other external contaminants. When this is necessary, a Class 1 termination is used. Also, Class 1 terminations can provide a means of maintaining pressure in a cable if it normally operates under pressure. Regardless of which class of termination is used, the cable's metallic shield must be grounded. Grounding the shield is important to protect personnel working on the cable from a shock hazard. Different methods of grounding can be used, depending on the cable's design. For example, on cables with concentric neutral wires, the concentric wires are often connected directly to a ground wire. On cables with a metallic ribbon, an extension wire is generally attached to the ribbon and then to a ground source. When you're making a termination, be certain you know and follow your company's procedures for grounding the metallic shield. In this first part of the program, we've taken a brief look at what terminations are, the protection they provide, and how terminations are classified. We saw that there are three basic classes of terminations, and that each provides a different degree of protection. In the next part of the program, we'll look at a tape termination. Before you go on, however, take some time to read over the material on termination classes in your textbook and answer the questions. In the last part of the program, we looked at the function of a primary cable termination and at the three classes of terminations commonly used on primary cables. For any type of termination, you need to know the size and type of cable you'll be working with and the system voltage the cable will be handling. In this part of the program, we're going to look at a tape termination. We'll watch as a crewman installs a 15 kV termination for connection to a pad-mounted transformer. Remember, the steps we'll see are general procedures. You should check your company's procedures for the methods you should use. Now let's join the crewman at the job site. When this cable was installed, enough slack was left so that it could be properly trained after the termination is made. One of the first steps in making the termination is cutting the cable to its specified length. After the cable has been cut, it's secured so that the cable end can be prepared. Preparing a cable involves removing the various cable layers according to a specific set of instructions. Following these instructions is essential to ensuring that the termination is made correctly. For this example, the first layer to be removed is the cable jacket. The workman first measures the proper distance and places a mark on the cable jacket. He then cuts around the cable at the marked distance, being careful not to cut through the jacket to the layers beneath. After this is done, he slits the jacket from the first cut back down to the cable end. Once the cuts are made, the jacket is removed, exposing the metallic shield. The next step is removing the metallic shield layer. The proper distance is measured and marked with tape. Then the metallic shield is cut at the tape mark and removed. The next layer to be removed is the semiconductive insulation shield. Again, a ruler is used to measure where the insulation shield will be cut. Removing the insulation shield exposes the insulation layer, which will be removed next. Often, the amount of insulation that has to be removed to install the connector is indicated in the instructions. If it isn't, you can measure the connector first and then measure the cable. Then the insulation and the semiconductive conductor shield are cut. Care should be taken not to nick the conductor with the cutting tool. After he makes the first cut, the workman makes a second cut lengthwise back to the end of the cable, and then removes the insulation and the conductor shield. The next step is penciling or tapering the insulation. To protect the conductor during the penciling process, a layer of vinyl tape is applied. Tapering the insulation provides a smooth transition between the cable insulation and the tape insulation that will be applied later. A measurement is taken to determine how far back to taper the insulation. Then, the worker tapers the insulation toward the conductor to the specified slope. When the insulation is tapered, the vinyl tape is removed and the workman brushes the conductor for a good electrical connection. He then places a compression lug on the conductor and crimps it using the correct press and die. Next, the insulation is sanded with a non-conductive sandpaper to remove any trace of conductive material. This minimizes the possibility of tracking between the cable conductor and the insulation shield. The penciled insulation is sanded to smooth out the taper. Then the compression lug is filed to remove any sharp edges created by the compressions. Next, the cable insulation is wiped with an approved solvent and a clean cloth to remove conductive contaminants. With the connector in place, the next step in the process is building the termination using various types of tape. The termination instructions provide detailed information about the types of tape that should be used and the methods for applying them. The first layer to be applied is a rubber insulating tape. The rubber insulating tape is applied starting at the insulation shield and moving toward the lug. The tape is used to build up additional insulation in the shape of a cone. The cone should be tapered evenly at each end. Its diameter at the center should be built up to the dimensions specified in the instructions. The actual size of the cone will depend on the voltage that will be applied to the cable and on the type of cable insulation. When the cone is complete, semiconductive tape is applied to restore the function of the semiconductive insulation shield that was removed. The semiconductive tape is applied using half-lap layers, beginning at the insulation shield and extending to the widest part of the cone. The tape effectively extends the cable's insulation shield over the larger area of the insulation buildup. Over the semiconductive tape, the workman then applies a layer of conductive metallic tape, which bleeds off static charges from the semiconductive tape. The metallic tape is started at the widest portion of the cone, run down the cone, and overlapped around the metallic shield layer of the cable. After the metallic tape has been applied, the metallic shield has to be grounded. To ground the metallic shield at the termination point, an additional wire has to be attached to the shield and then connected to an electrical ground. When this connection is made, it's a common practice to join the conductive tape to the shield using solder. The solder uses a chemical agent called flux to help the metals adhere to each other. When you're soldering, it's important that you don't overheat the area of the cable being soldered. Excessive heat could damage the layers beneath the metallic shield. When the metallic shield has been properly soldered, it's covered with plastic tape to provide mechanical protection. A second, smaller cone is then built near the end of the cable to increase the creepage distance between the conductor and the insulation shield. It also seals the cable end. To build this cone, semiconductive tape is first applied over the lug barrel and over any areas of exposed conductor. Then, rubber insulating tape is applied to build the cone. The rubber tape is applied over the semiconductive tape from the connector barrel back to the top of the tapered area of insulation. When the second cone is finished, the termination is completed by reconstructing the jacket layer of the cable with 2 layers of plastic insulating tape. The first layer is applied over the entire length of the cable, from the end of the lug back to the termination point. Then the second layer is applied. To ensure a good seal, the top of each tape lap is covered when another layer is applied. This will help protect the cable termination from water after it's installed. When the plastic tape has been applied, the tape termination is complete. There are other methods of building a tape termination. The example we used was designed to show the basic steps that are involved. An alternative to using a tape termination is to use a prefabricated kit. When we come back, we'll look at an example of such a kit. An alternative to the tape termination we saw earlier is a termination kit. Termination kits usually have preformed parts that are installed at the end of a prepared cable. In this part of the program, we'll be looking at one type of termination kit called an elbow termination. We'll see where elbow terminations are commonly used, how they're constructed, and how they can be installed. Earlier in the program, we said that the environment in which a cable is used is one factor in determining the type of termination that's needed. Another factor is whether the cable is used in an underground, overhead, or URD application. In URD work, for example, insulated terminations are commonly used. An insulated termination is one in which the connection point between a cable and a piece of equipment is insulated. Typically, URD equipment has bushings that require elbow terminations. An elbow termination provides a fully insulated connection between the cable and the equipment. There are two basic types of elbow terminations: load break elbows and non-load break or dead break elbows. From the outside, they look similar, but they're designed to work differently. Load break elbows are designed to interrupt the flow of current. They're typically used as switching points between cables and pieces of equipment. For example, a pad-mounted transformer can be de-energized by removing a load break elbow. The non-load break elbow, on the other hand, is designed to serve only as an insulated connection between a cable and a piece of equipment. It is not designed to be switched under load. To get an idea of how the two elbow terminations differ, let's look at an illustration of each, beginning with the load break elbow. This is a typical load break elbow. It consists of a connector, a conductive insert shield, a layer of insulation, a layer of semiconductive material, a grounding eye, a pulling eye, a male probe contact, and an arc extinguisher. Let's take a brief look at each of these parts. The conductive insert shield surrounds the area where the cable connector enters the elbow. The layer of insulation over the conductive insert shield insulates the connection to the equipment. The layer of semiconductive material over the insulation layer reduces areas of stress concentration on the insulation. Any static charge that builds up on the semiconductive material is bled off to the cable's metallic shield layer through the grounding eye. The pulling eye is where a hot stick can be attached to control the elbow during switching. The male probe contact is where the elbow is connected to an equipment bushing. One end of the contact has a threaded screw, which is used to hold the contact in the elbow. On the other end of the male contact is a plastic tip, which serves as an arc extinguishing device when the elbow is removed from equipment under load. The non-load break elbow has a similar construction, but its male probe contact does not make an electrical connection between the cable connector and the electrical equipment. Instead, the internal parts of the non-load break elbow are mechanically bolted together at the contact points. This is an illustration of an unassembled non-load break elbow. The male probe contact is a short, threaded piece that screws into a bushing designed for non-load break use. And you can see that there is no arc extinguishing device. So, to remove a non-load break elbow, you first have to remove the load from the cable and equipment. The elbow also has a rubber end cap that's installed as an additional sealing device after the connection is made. Okay, now that we've seen how the two types of elbows are constructed, let's watch as a load break elbow is prepared and installed on a typical URD pad-mounted transformer. The elbow will be installed on a cable with a concentric wire metallic shield. The workman first checks the elbow termination kit to make sure that it's the right one for the cable it will be installed on. He'll also make sure that the connector provided in the kit is the correct size for the cable he's working with. Once he's determined that he has the right kit for the job, the worker trains the cable, leaving enough slack in the cable to make the termination. The workman begins the termination by placing a mark on the cable at a point 9 inches from the center of the transformer bushing. This distance ensures that there will be enough of the concentric wires remaining to reconnect after the termination is complete. The concentric wires are then unwrapped and secured out of the way before the cable cut is made. Next, the cable is marked 9 inches from where the concentric wires were secured, and then cut. Then the conductor is exposed 1 inch from the cable end. This allows room for installing a compression connector. The cable conductor is cleaned with a wire brush to ensure good electrical contact. Before installing the connector, he makes sure that the connector eye is facing the transformer bushing. Otherwise, it would be difficult to install the termination onto the transformer. Then the connector is crimped onto the conductor. The first crimp is made at the top of the connector, and the remaining compressions are made working back toward the cable insulation. After the connector has been installed, it's filed to remove any sharp edges caused by the press and die and to smooth the surface of the connector. The next step is to remove the cable's insulation shield layer. Following the instructions, the workman measures from the center of the connector eye to a designated point. After marking the appropriate spot, he cuts the insulation shield. As always, care must be taken when cutting into the insulation shield layer so that the primary insulation beneath it is not damaged. After the insulation shield is removed, the workman uses non-conductive sandpaper on the primary insulation to remove any traces of semiconductive material. He also uses an approved cleaning solvent to clean the cable insulation. Once the insulation has been cleaned, it's coated with a silicone grease. This grease is generally supplied in the termination kit. The grease provides lubrication so that the workman can slide the preformed elbow over the compression connector and the primary insulation. He pushes the elbow termination onto the cable so that the connector eye is facing the bushing cavity. The bushing cavity is where the elbow makes contact with the equipment. By looking through the bushing cavity, the workman can see when the cable is fully inserted into the elbow. When the elbow is in place, the male probe is screwed into the connector's threaded eye. The probe is installed by hand and then tightened down. The only step remaining is grounding the outside of the elbow. This is done by taking 2 strands of the concentric neutral wire and feeding them through the grounding eye of the elbow. The cable's concentric wires are then connected to the grounding lug, which is connected to a known ground source. This grounds the outside layer of the elbow and completes the termination. The termination we just saw is typical of URD elbow terminations, but connectors, installation tools, and procedures can vary, so be sure to check with your company for the proper techniques and equipment. In this part of the program, we saw that there are 2 types of elbow terminations, load break and non-load break. Both types of elbows provide an insulated connection point between a cable and its connected equipment. The elbow is only one type of termination, however, and it's designed primarily for URD applications. When we come back, we'll look at another type of termination that's used at pole-top locations. For now, read over the information on elbow terminations in your textbook and answer the questions. As we've seen, where a termination must be located often affects the kind of termination that's used. And in the last part of the program, we saw that where the termination is used can also be a determining factor. In the last part of the program, we saw elbow terminations, which are designed to provide insulated connection points. In this part of the program, we'll look at a termination that has exposed, energized parts. We'll see how this termination is installed at a pole-top location. A pole-top termination, typically called a pothead, is generally used where an underground system is joined to an overhead system. These terminations are often in open areas where contamination is likely. Contaminants like dirt and salt can lead to tracking. To reduce tracking, terminations are often designed with insulator skirts, like these. The skirts are designed to break contamination paths. They reduce the ability of current to track along the length of the termination. Another way these terminations reduce tracking is through the material used for insulation. Two track-resistant materials commonly used are porcelain and silicone rubber. In this part of the program, we'll be looking at a type of porcelain-insulated terminator. We'll see how the terminator is designed and how one is installed at a pole-top location. First, let's look at the terminator itself. This is a typical porcelain terminator that's filled with an insulating fluid. It has insulator skirts, a mounting bracket, a sealing plug which covers a drainage hole for excess insulating fluid, a set screw and lock nut for tightening down the conductor after it's in place, and the cable entrance. This terminator is part of a kit which also contains a plastic bottle and a connector. The plastic bottle is used to collect the insulating fluid that's displaced from the terminator when the cable is installed. Okay, let's see how this terminator can be installed. In our example, the terminator will be supported on a pole by a galvanized steel mounting bracket. After checking to make sure that he has the right terminator for the size and type of cable he's working with, the workman removes a nut on the mounting bracket, secures the terminator in place, and then replaces the nut and tightens it down. Then the cable is held alongside the terminator and marked with a wire. The wire indicates the point to which the concentric wires will be pulled back before the cable is cut. This ensures that enough of the concentric wiring will remain after the final cable cut is made. After the concentric wires are pulled back, another mark is made to indicate where the cable is to be cut. Then the cable is cut to its final length and the cable layers are prepared according to the termination instructions. Now, before installing the connector, the workman checks the instructions for the correct press and die information. Then he wire brushes the conductor to ensure good electrical contact. Then the connector is installed and compressed. The workman is careful to keep the connector straight, and he rotates the press after each compression. When the compressions are complete, any sharp edges on the connector are filed and the connector is cleaned. The end of the insulation is then tapered so that it's the same diameter as the connector. The area between the connector and the insulation is then filled with an insulation compound, which is generally supplied in the termination kit. The compound establishes a smooth surface on the insulation and on the connector. After the compound is applied, it's covered with 2 layers of vinyl tape for mechanical protection. Now, a measurement is taken from the end of the connector, and the semiconductive insulation shield is removed. The workman is careful not to damage the primary insulation when he removes the insulation shield. Then the insulation area is sanded to remove any semiconductive particles or contaminants. Next, the cable is measured and a tape mark is placed on the cable to indicate how far into the terminator the cable must be inserted. The next step is to install the plastic bottle in the terminator housing. The bottle collects displaced insulating fluid as the cable is installed. Next, the cable insulation and connector are cleaned with an approved cleaning solvent. Then the cable insulation and the connector are coated with silicone grease. Some kits may include plastic gloves to apply the silicone grease. This avoids the possibility of contaminating the cable with dirt or other materials that might be on the workman's hands. To insert the cable, the plug at the base of the terminator is removed. Then, with a constant force, the cable is pushed up until the tape mark is even with the bottom of the terminator's cable entrance. Inserting the cable displaces the insulating fluid from the terminator into the plastic bottle. With the cable fully inserted, the set screw is tightened to secure the cable in the terminator. Then the lock nut is tightened. Then the bottle is removed, and the sealing plug is reinstalled and tightened. The concentric neutral wires are then bundled together and connected to the pole ground. This provides the necessary ground to bleed off any static charges on the insulation shield. The terminator we just saw is only one type of porcelain terminator. Your company may have different ones, but the principles and installation procedures will be pretty much the same. In this part of the program, we've looked at a porcelain terminator designed for use on a pole, where there's exposure to the elements. We saw that the porcelain terminator provided stress control and tracking protection. In addition to porcelain, silicone rubber terminators are also suitable for pole-top work. We'll look at a few of those when we come back. In the last part of this program, we looked at one example of a porcelain termination. We said that for terminations exposed to the elements, two materials were commonly used. One is porcelain, and the other is silicone rubber, which we'll be focusing on in this part of the program. We'll be looking at three different types of silicone rubber termination kits and seeing how they're installed. Each of these kits includes a detailed instruction sheet. The instructions must be understood and followed carefully to ensure that the termination is installed properly. The first termination kit we're going to look at is a molded slip-on termination. Let's see what this kit looks like with a simplified illustration. The slip-on termination has a molded rubber stress cone. The cone works similarly to the stress cone that was built for the tape termination. Attached to the stress cone is a metal grounding strap, to which the concentric wires are attached for grounding the termination. The kit also includes a layer of skirted insulators to provide protection against tracking, and sealing tape to protect the termination from contaminants. Let's see how this termination is installed. This worker has already cut off the concentric wires and removed the semiconductive insulation shield, the primary insulation, and the conductor shield layers. He's also cleaned the cable insulation, tapered it, wire brushed the conductor, and covered it with tape. To make it easier to slip the stress cone onto the end of the cable, the worker applies a silicone grease to the cable insulation and then to the stress cone. With the silicone grease on the insulation, he slips the cone onto the cable. Then he positions the end of the cone so that it butts up against the semiconductive insulation shield. He then unrolls the end to overlap the insulation shield layer. After removing the protective tape, the workman installs the connector. He crimps the connector onto the conductor according to the termination instructions. The stress cone supplies the end of the cable's insulation shield with a means of stress control protection. But for terminations that may be exposed to contamination, a source of tracking protection must also be provided. In this example, tracking protection is provided by a skirted cold shrink tube. As you probably know, a cold shrink tube is a rubber tube that shrinks down over the cable when a plastic tab is pulled. The workman installs the cold shrink tube by placing it over the end of the cable so that it overlaps the stress cone. When the tube is in place, he pulls the plastic tab. The tube shrinks onto the end of the cone and onto the cable's insulation, creating a seal between the rubber insulator and the stress cone. Then the workman seals the end using a silicone tape. Finally, he attaches the concentric wires to the grounding strap to ground the termination. This is a Class 1 termination because it provides stress control through the cone, external leakage protection through the skirted insulators, and a seal against the environment with the silicone tape. The next type of termination we're going to look at is a single-piece cold shrink tube. This type of termination uses a method of stress control that's a little different from the one we've seen so far. Earlier in the program, we said that there were two types of stress control. One type uses a cone to build up insulation and thereby spread out the concentration of voltage stress. The terminations we've been looking at so far have all used this method. The second method uses a special material to reduce stress concentration. This method is called the capacitive stress control method. To see how it works, let's take a look at an illustration. The cold shrink tube consists of two layers. The inner layer is made of a special material that has a high ability to store a charge. This material has what is called a high dielectric constant. A material's dielectric constant is given as a K factor. The higher the K factor, the greater the material's ability to store a charge. Air, for example, has a K factor of 1. Cable insulation has a K factor of around 3. This special cold shrink inner layer has a K factor of 30. When a material with a high K factor is placed over the end of the semiconductive insulation shield, the stress concentration on the insulation is reduced. How this reduction is achieved would require a detailed discussion of electrical theory, but we can say that when a high K factor material is used, it spreads out the voltage stress at the end of the cable shield so that it's effectively reduced to an acceptable level. The outer layer of the cold shrink tube is insulation material. It provides a skirted insulator between the conductor and the grounded insulation shield. Let's see how this type of termination can be put on. To begin this job, the workman ties the concentric wires back at a specified distance and cuts the cable to its final length. After he removes the cable layers, the workman installs the connector. He then files the connector to remove any rough edges. He sands the cable insulation and then cleans it with an approved solvent. Next, he applies a silicone grease to the primary insulation. In this example, the silicone grease is not being used as a lubricant. Instead, it serves as a filler and a sealant between the cable layers and the cold shrink tube. The workman places the cold shrink tube over the insulation and applies it. He places the tube so that it butts up against the concentric wires. The last step is to ground the termination by connecting the grounding strap on the cold shrink terminator to the concentric wires. To mount the terminator, the workman installs a metal mounting bracket and then mounts the terminator. The result is a one-piece Class 1 termination that provides stress control, external leakage protection, and an end seal. The last type of rubber termination that we'll look at is applied using heat shrink tubes. Heat shrink tubes are made of a material that shrinks down when it's heated. Like the cold shrink tubes we've seen, this heat shrink tube works by the capacitive stress control method. Let's see how it's applied. As with all kit terminations, an important first step is to read and understand the kit instructions. Here, the cable has been prepared and the connector lug has already been installed. The next step is to apply a putty that's supplied in the kit. The workman wraps putty around the cable to provide a smooth transition between the end of the insulation shield layer and the primary insulation. He then positions a stress control tube so that it overlaps the insulation shield and the primary insulation. The workman applies the tube using an approved heat source. He uses a brushing motion to ensure that the heat is applied evenly. He applies heat until the tube conforms to the contour of the cable. After the tube is in place, the workman cleans it using an approved solvent. Then he applies a layer of red sealing putty to the cable's metallic shield. Next, he positions a second heat shrink tube at the edge of the red sealing putty. This tube provides insulation. This tube is also applied using an approved heat source and a brushing motion. The tube is properly applied when it appears smooth and wrinkle-free. Again, after the tube is in place, the workman cleans the cable with an approved solvent. Then he applies 2 other layers of red sealing putty. He applies the first layer over the heat shrink tube and the second layer over the connector. This second layer is applied so that it's the same thickness as the cable insulation. Next, the workman applies the final heat shrink tube using the same brushing motion and approved heat source. To increase the insulation externally and to guard against tracking, the workman installs heat shrink insulation skirts over the tubes. The positioning and number of skirts will vary depending on the voltage that will be applied to the cable conductor. When the skirts are in place, the workman completes the termination by grounding the cable's metallic shield. In this part of the program, we've taken a look at 3 types of silicone rubber Class 1 terminations. Like the porcelain terminations we saw earlier, each is designed to be used in areas where the termination is exposed to the elements and contamination. All of the terminations we've seen so far have been on cables with some form of rubber or polyethylene insulation. In certain areas, however, a cable with a different construction is used. In the next part of the program, we'll see how terminations can be made on this other type of cable. Before you go on, however, take some time to read over the material on rubber terminations in your text and answer the questions. In this part of the program, we're going to look at a cable that's constructed differently than the cables we've seen so far. We'll be looking at a paper-insulated, lead-covered, or PILC cable. We'll see what makes this cable different, and we'll look at some of the considerations and techniques for making a termination on PILC cable. To begin with, let's look at the differences between this cable and the other cables we've seen. The basic construction of the cable is similar. There's a conductor shield, insulation, and an insulation shield. But the insulation is made up of multiple layers of paper tape that are wrapped around the shielded conductor. The number of paper tape layers used is appropriate for the voltage to be applied to the conductor. The tape is saturated with a liquid insulating compound such as mineral oil. The oil-impregnated paper is a very efficient insulator. Over the paper insulation is the semiconductive insulation shield, which helps to even out voltage stress within the insulation. With some cable designs, like this 3-conductor cable, there may also be a metallic shield in the form of a tape ribbon. On other cables, the lead cover serves as the metallic shield. Because the paper insulation is vulnerable to damage caused by water or corrosives, the cable is enclosed or jacketed with lead. The lead covering is flexible to allow it to be bent during installation, and it's very effective in preventing damage to the paper insulation. Because of the differences between PILC and other types of cable, there are several special techniques and tools for constructing terminations for PILC cables. To see what some of these tools and techniques are, let's watch one method of preparing a termination. In this example, we'll be using a porcelain termination kit on a single conductor PILC cable. The termination will be made on the ground, but it's designed for a pole top application. As before, reading the termination instructions is essential for making the termination correctly. The first step is determining how much of the outer cable jacket and lead to remove. To do this, the terminator connector is temporarily installed in the porcelain housing to see how far into the termination the cable will go. A nut holds the connector in place. The workman takes a measurement from the inside of the top of the connector down to the bottom of the metal terminator housing. He then marks the cable at the specified distance, allowing about 3 extra inches to make sure the jacket will be away from the termination area. Next, he cuts the cable jacket and removes it. After checking the directions, the workman measures the cable and scores it at the point where the lead cover will be removed. In this case, the measurement will allow 1 inch of the lead cover to extend up into the terminator. The workman then cuts the lead cover using a chipping knife, which is sometimes called a hack knife. He's careful to avoid nicking any of the layers beneath the lead during this process. Next, he uses a wire brush to clean the remaining lead area. This will help the solder that will be used later adhere to the lead. A solid flux material is then applied to the lead layer. The flux material will help later when the cable connector is soldered in place. With the flux applied, the lead cover is removed from the score mark to the end of the cable. Now, to protect the paper insulation below, a protective tape is applied over it. Next, he measures the connector and marks the appropriate distance on the cable insulation. He then removes the remaining cable layers, exposing enough bare conductor to install the connector. The conductor is then wire brushed. Next, the cable is repositioned to make the conductor end more accessible. The connector for this termination is not a compression type, as we've seen before. It's designed to be soldered to the conductor to make a solid electrical connection. The workman first coats both the connector and the terminator wiping sleeve with solder. This process is called tinning. Now, before the connector can be installed, a couple of additional things need to be done. First, the workman places the wiping sleeve over the cable end. Then he applies flux to the conductor. The workman then puts the connector in place and wraps a fire-retardant cloth around the bottom of it. He wraps the cloth around the cable in the area between the connector and the cable insulation. The cloth will stop the melted solder that will be used to install the connector. Then a torch is used to heat the connector. Wire solder is fed through the top of the connector through openings called soldering holes. The heated connector and conductor cause the solder to melt. The melted solder runs down inside the connector and between the conductor strands, forming a solid metal mass. When the connector will not take any more solder, the soldering is complete. After the solder has cooled, the workman removes the fire-retardant cloth and wipes the area around the connector to remove any excess solder. After repositioning the cable and installing the terminator housing, the workman removes the protective tape layer and the semiconductive insulation shield. The top layer of the paper insulation is also removed. This ensures that there won't be any semiconductive materials left on the paper insulation. The top layer of insulation is replaced with insulating tape. The workman uses the same insulating tape to build a stress cone. He begins the cone at the edge of the lead layer and builds it up until it conforms to the size and shape specified in the instructions. He then extends the cable insulation shield to the top of the cone by applying a braided metallic shielding tape. Beginning at the middle of the stress cone, he half-laps the tape back to the lead cover. He applies flux to the braided tape and then tacks the braid to the lead cover to form a ground connection. Next, the workman slips the terminator housing over the cable and connects it to the wiping sleeve. And he installs a hood nut and rubber gasket at the top of the terminator housing. Now, the bottom of the termination needs to be sealed. To do this, the workman wraps a lead spacer around the cable and works it into the end of the wiping sleeve. The spacer will help seal the wiping sleeve during the soldering process. Next, he places a solder restraining tape on the wiping sleeve and on part of the exposed lead to narrow the area where the solder will be applied. Then the melted solder is poured around the metal base, and a fire-retardant cloth called a wiping cloth is used to wipe the solder around the sleeve. A solid metal seal is formed as the solder adheres to the tinned metal terminator base. To smooth out the solder, the workman uses a torch to reheat the sleeve, and he wipes the solder again. After the seal is complete, he attaches a ground wire to the lead cover and solders it in place. At this point, the procedures for this company call for the terminator housing to be filled to a specified air pressure and coated with a soapy solution to check for leaks. Then the solder restraining tape is removed. The final step is filling the terminator with a sealing compound. To do this, the cable is placed upright and the hood nut assembly is removed. Then, a pipe and funnel assembly is installed. The sealing compound serves a number of purposes. First, it provides an enclosure to keep the oil on the paper insulation. The sealing compound also prevents contaminants from getting inside the termination. Before the compound is poured into the termination, the metal housing may have to be heated to ensure that its internal parts are not cold. Cold spots inside the termination could cause the heated compound to cool, leaving voids in the sealant. Also, while the compound is being poured, occasional heating of the pipe and the connector may be required to keep the compound liquid and to prevent the pipe from clogging. The workman pours in the compound until it reaches the top of the porcelain insulator. Then he tightens the nut on the connector again to keep the compound in the top of the termination. After the termination has cooled, the pipe and funnel assembly are removed and the plug is replaced. Finally, any excess compound that may have accumulated on the porcelain or other parts of the termination is wiped off. To connect the termination to other electrical equipment, a fitting called an aerial lug is used. An aerial lug screws onto the threads of the connector and is held in place by 2 bolts. So, as you can see, a termination on a PILC cable is quite different from the other terminations we've seen. The lead jacket and the paper insulation present different considerations, and they require different procedures, many of which require field experience to perfect. Keep in mind that the termination we saw is typical of those performed on PILC cables, but company procedures and equipment do vary. Before you begin a termination on paper cable, be sure to check your company's procedures. The terminations we've seen are typical of the ones you could be expected to make in the field. For the most part, each is used in a different application, but many of the basic principles and procedures are the same. An understanding of these terminations and a knowledge of how they can be installed are essential for anyone who works with and maintains primary cable.